Ladies and gentlemen, welcome to the talk on Loki, hardening code obfuscation against automated attacks. Let me stress, this is your unique opportunity to listen on code obfuscation because this is the only talk speaking about code obfuscation and deobfuscation at USENIX this year. So, in the next 10 to 12 minutes, we will learn what VM-based obfuscation is, how automated attacks can break all these state-of-the-art VMs, and how we can do better to harden our code obfuscation. For those of you who are not that familiar with obfuscation, it's the process of transforming code to make it harder to analyze, to make it unintelligible, and the goal is to complicate reverse engineering attempts. This is done in a wide array of applications, mostly in industry for protecting intellectual property. Think about digital rights management, but also in abuse prevention, for example, Google's BotGuard. But there's also a dark side. Malware authors use obfuscation to conceal the malicious payloads of their malware. In this talk, we are going to look into VM-based obfuscation, which is just a single technique, but it's one of the most powerful ones and is universally used in most state-of-the-art tools. The basic idea is you have your code here. You have some intellectual property in that code that you would like to protect. Right now, when compiling the binary, it's easy to analyze the code, right? Just disassemble it, look at it, and you can understand it as an attacker. So what we do is we make up a new instruction set architecture, and we transfer our intellectual property from the normal code, so to speak, into this new instruction set. We then replace our original code with a VM interpreter that knows how to interpret this made-up instruction set. And now the attacker has a blob of data they cannot understand because they don't know this instruction set. But there's one downside. The interpreter must know how to run our obfuscated code. So an attacker can simply focus on this VM interpreter. How would you go about doing that? Basically, you would first locate all the VM interpreter components, and then you would simplify the individual handlers using some program analysis techniques. And once you understood all the handlers, you can simply reconstruct the original code. In this talk, we'll focus on the simplification on the handlers, on the automated simplification of the handlers, and then we will see how we can do better and harden our handlers again. So, when attacking these VMs, there are three broad categories. First, we can remove instructions that do not contribute to the handler's computation. We can symbolically execute the handler, or we can use program synthesis. Starting with instruction removal, here we have a handler on the left side, and when applying compiler-like optimization passes onto this, for example, dead code elimination, constant folding, constant propagation, or peephole optimization, as you can see, we can get rid of most of the instructions and boil it down to a mere 3 instructions in the handler. This may sound simple, but it's actually a very powerful technique, and you can come by and try this on most state-of-the-art tools and get surprising results. The next tool in the attacker's arsenal is symbolic execution. So when symbolically executing the handler, we have here, we walk it down and we negate the symbolic register RCX. We negate it as well again. And our symbolic execution engine has a simplification rule. Negating twice yields the original result. So we know here it's still RCX. Then we add RCX to itself, and we might have another simplification rule that tells us this is a left shift by 1. With that, we can symbolically summarize what the handler is actually doing. Now, the last technique, and probably the most powerful one, is program synthesis. Here we have a handler f, which is represented as a mathematical function, and we don't really want to know what's going on there. It looks really complicated, right? We don't care. So instead, what we do is We use it as a black box, we sample some inputs, and we record the output. This is called an input-output pair. We do this multiple times, recording multiple input-output samples, and then we learn a new function h that has the same input-output behavior. So the idea is, if it behaves the same on all inputs, it is the same. And as you can see, x plus y plus z is significantly more simple than our original function. Now, with these three techniques, we can simplify state-of-the-art VM obfuscation schemes. So the question really is, can we do better and how? And that's why we came up with Loki. We have three core techniques that we use to make these obfuscation schemes harder. So we merge core semantics, we use complex target-specific expression, and we apply Mixed-Boolean Arithmetic in a clever way. If that doesn't make sense right now, it will in a couple of seconds, I promise. So, merging core semantics. We again have our handler as a mathematical representation. And what the handler does, its core semantics, here for the function h is x plus y, is rather simple. To make this more complex, our first idea is to merge multiple of these core semantics into a single handler. Here, we do need a key to allow us to address the individual semantics. Now, with these key-dependent core semantics, the handler is already more complex, but we can do better. If we think about this in terms of the control flow, it would look like something like that. We have the if, and we have either the first core semantics or the second core semantics. But really, what we would love to have is a single large block, so a single large basic block, and turns out we can achieve that rather simply using a so-called polynomial encoding. So instead of having the if, we use multiplication and addition to achieve the same. This leads to a very tight interlocking of the core semantics, which makes them significantly more complex. Now, we can do even better here, and we can look at our key selection, which allows us to address the individual core semantics and make that more complex. For example, we can use mathematically hard problems, such as factorization, or we can use point functions to prevent static attacks. There is more to this, however, for the full details, feel free to check out the paper. Now, this only works for static attackers, so we are still facing the more powerful dynamic attacker. And to stop program synthesis, here's a simple idea. Instead of having these generic core semantics like an addition and a multiplication, which we call sequentially, we combine them into a single core semantics, which does all of them. Back to our mathematical representation of the handler, this would look like this. Instead of having x plus y, we have something more complex, semantically complex. And the important thing is we can get this from the target program. So this is target specific depending on the code we want to obfuscate. And the very nice thing here is it is very well suited to defeat program synthesis. Now, one attack vector is left, and that's symbolic execution. So the idea to defeat symbolic execution is to increase the syntactic complexity. Instead of having our core semantics in this very simple form, we can make this more complex. This expression still computes the same, but is more complex to analyze. And this complexity helps defeat symbolic execution. Now, how would we go about building one of these syntactically complex expressions? That's where Mixed-Boolean Arithmetic, or MBAs for short, come into play. Imagine this expression on the left-hand side, which we want to obfuscate, and a couple of rewriting rules we have where we map a simple identity onto a more complex one. So we'll pick some sub-expression, we look that up, and we replace it, making the expression more complex. And traditionally, this would be how we would apply an MBA. The neat thing is they are still equal, still the same computation. So this traditional approach is bad for two reasons. First, we have like about 50 rewriting rules which are handcrafted. Instead, what we propose is to use enumerative program synthesis up to a certain depth and find like 850,000 expressions, making this a lookup table with all identities up to this depth. And second, instead of being done after one simple replacement, we can recursively keep going, producing expressions of infinite complexity. And with this recursive rewriting, we are done to prevent symbolic execution. Now, putting it all together, the combination of our techniques is suited to prevent all attacks, to make the attacker significantly weaker, both in a static and dynamic scenario. And with that, let's wrap it up. We have seen automated simplification can defeat VMs. However, there's a couple of techniques we can use in combination to prevent this. And if you're interested in that, feel free to check out the paper or head to GitHub, check out our artifact. It's available there. All right, with that, I'm open to questions both online right now or later offline.